Okay, I'm just going to go through the first 8 multiple choice questions in this video, and then the remainder will be in the next one. Okay, so question 1. So we've got a calculation, and I'm not going to do a full quens on this one, but let's just have a look at the quantities we've been given. So we've got a current of 2 amps. Okay, so we're looking for an equation with current in, flows in a circuit. How much charge? Okay, so we're looking for an equation with current, charge or charge flow, and then we've also got a time. So we're looking for an equation with current, charge and time. And if we go to our formula sheet, and you'll see that's the first one in the electricity topic, charge flow equals current times time. I'm just going to use the symbols Q equals I times T. Okay. So Q for charge equals current times time. And the thing to just be aware of here is, I'm not doing full quens, but I still need to check the units. Okay, so I've done, these are my quantities, the U in quens is the units, and for this time I'm going to need to convert that into seconds. Okay, what you'll notice with multiple choice questions is they'll always have one of the answers that looks right at a first glance, but has involved you making basically a mistake. Okay, so if you look at this one, you'll see that if you do 2 times 3, you'll get 6, which is one of the answers, but it's incorrect, okay, because we haven't converted the units. So let's just put the values in then. So it's going to be, Q is going to equal 2 times 180, which is going to give us 360 coulombs. So the correct answer is D. Right. Question 2, we've got some magnetic field lines, and the couple of two key things to remember here. 1, magnetic field lines always run from north to south. Okay, they always run away from North Pole. So this one is incorrect because we've got field lines going into a North Pole, which is wrong. This one is also incorrect because we've got field lines coming out of this South Pole, which doesn't happen. Okay, so we've reduced it down to C or D. The second thing we're going to remember is that when you have opposite poles, like we have in both of these, the result is that you'll get an attractive force between them. Okay, opposite poles attract each other. Okay, this is what they would look like if opposite poles repelled each other, which they don't. Okay, so this is the correct answer. This is showing opposite poles. The field lines are going out of the north, they're going into the south, and this is showing them attracting. Okay, the field lines actually show the direction that the North Pole will experience a force. So as you can see, this North Pole is going to want to travel along those field lines towards the south, and the South Pole always would move in the opposite direction to the field lines, which is towards the North Pole. So they're going to meet in the middle, as you'd expect. So the correct answer here is D. Okay. Question 3 is another calculation. So we're calculating potential energy. We've been given some different quantities. So we've got a mass of 65 kilograms. We've got 50 steps, and each step is 0.3 meters high. We're going to need both of those values, and we've been given that the gravitational field strength is 10 newtons per kilogram. So the energy, the gravitational potential energy, is going to equal the mass, 65, multiplied by the height, and that the height is, well, they're climbing up 50 steps, and each step is 0.3 meters high. So I'm going to multiply those two values together. That's going to be the total height, and then I'm going to multiply it by the gravitational field strength, which is 10. Okay, and when you put all of those values in, you should get 9,750, which is answer B. Okay, so that's the correct one. Question 4, a student holds a balloon near a narrow stream of water from a tap. The water is attracted to the balloon. Okay, so we've been told what the outcome is. There's a force of attraction. Okay, the thing we need to remember with charges is similar to how magnets work. With magnets, if you have opposite poles, they attract, and the same poles or like poles repel. The same is true of charges. Opposite charges attract, and the same charge or like charges repel. Okay, so we're looking for one of the answers that basically has opposite charges in. Here they've got the same charge, so it can't be A because they would repel. The water would be repelled in that case. If the water and the balloon were both positive, it would also repel. If the water and the balloon were not charged, then there wouldn't be any force at all, so it wouldn't be attracted or repelled. So the only one it could be is that the water is positive and the balloon is negative. Okay, so that's our correct answer, D. Okay, question 5. We've got a force extension graph and we're asked to just sort of say what's going on in part P and part Q. So in part P, basically the options we've got are either linear or non-linear. Linear means it's a straight line, so you can see that it's got to be either A or B. Okay, so we've narrowed it down. It can't be those two because section P is a straight line. It's linear. Linear means line. And then Q, we're asked to describe this in terms of its properties here. Is it behaving in an elastic way or a plastic way? Well, actually, when a material is behaving elastically, that means that when you remove the force, it will go back to its original length. That actually is happening where the graph is linear. So it's elastic in section P, and in section Q it's not linear, which means that it must be behaving plastically. Okay, so that rules out A because it's not elastic in part Q, otherwise it would also be a straight line. Okay, so the correct answer here is B. All right, question 6. We've got a heating curve. We're heating up a substance from solid to gas. So here it is as a solid. I'm just going to put S for solid. During section B, it's a liquid getting heated up, and then at section D, it's a gas. It's become a gas and it's getting hotter. Okay. The bits we're interested in are the changes of state. So in part A, it's basically melting from a solid to a liquid. Notice how when you have a pure substance, as you melt it, the temperature doesn't change. Okay, all of the energy that's going in, we're still heating it up, but it's not getting hotter. Why? Because the energy is going into breaking the bonds that are holding it together as a solid. Okay, so melting involves bond breaking, and the bond breaking is where the energy is going. So rather than it getting hotter, it's breaking bonds. Okay, and then section C is again the temperature isn't going up because we're going from a liquid to a gas. We're boiling, evaporating, and again the temperature isn't going up until all of the liquid has become a gas because the energy is going into bond breaking as well. Okay. Here we're asked, so it's not going to be section B or D here because we're asked to find the specific latent heat of vaporization. So if we wanted to calculate the energy changes for sections B and D, we'd use the specific heat capacity of the substance as a liquid and the specific heat capacity of a gas. So whenever you're heating something up and the temperature is increasing, to work out the energy transfers, we use specific heat capacity. But when we're talking about latent heat, we're talking about a change of state rather than an increase in temperature. We're talking about a change of state. Okay, so the equation for that is the energy is equal to the mass of the substance multiplied by its latent heat, and that's different for different substances. And vaporization is referring to the change of state from a liquid to a gas or condensing back from a gas to a liquid. Okay, so that is part C on this graph. Okay, if the question is asked us to identify the part on the graph for the specific latent heat of fusion, that would be part A. Okay, so latent heat of fusion is for melting and freezing, and latent heat of vaporization is for boiling or evaporating and condensing. Okay, question 7. This is a moments question. We've got rotational forces and a pivot. Okay, and we've been asked to calculate the clockwise moment of the screwdriver about the pivot. Okay, so the clockwise moment is that one there. I'm going to call that capital M for moment, and we've been asked to find how big is the moment from that. Okay, so if you look on the formula sheet under forces, you will find the equation for moments. The moment of a force is equal to the force multiplied by its distance, and that's the distance in the direction 90 degrees to the force to the pivot. Okay, so it's the distance to the pivot. And you can write that as m equals F times d. That's how I'm going to write it. Okay, so the moment is equal to the force times the perpendicular distance. Well, the force is going down, so the perpendicular distance is just along the screwdriver, so that's nice and easy, which is 30 centimetres. Okay, so the moment is going to equal the force of 150 newtons multiplied by the perpendicular distance to the pivot here, which is 30 centimetres, but we need to convert that into metres because all of our answers are in Newton meters. Okay, so I'm going to convert that to 0.30 meters, and when I multiply those two together, I should get 45 Newton meters, which is answer B. Okay, and we didn't actually need to use that 0.7 value in the answer at all here, just to calculate the clockwise moment. If we wanted to find out how big the force was up on the rim of that paint lid there, then we could use that value for the 0.7, and actually the force there multiplied by 0.7 would be equal to the 150 times by 0.3. Okay, and what you find if you did that is that the force would end up being a lot larger than 150 newtons because of this leverage we get from the screwdriver. That's why it's a lot easier to open a paint can with a screwdriver with a long handle, because you can generate a much larger force if you're closer to the pivot. Okay, so yeah, but we don't actually need it for this question. Okay, final one from this video, question 8. We've asked to find which arrangement has the lowest resistance. So the key thing here is that when you add resistors in series, like in B, so one after the other, you add their resistances together, you increase their total resistance. Okay? When you add resistors in parallel, because you're providing more paths for the current to flow through, you can actually get more current through resistors when they're in parallel, which means that their overall resistance, which is the higher the resistance, the lower the current. If you can get more current through, that means that the resistance must be lower. Okay? So the more resistors you have in parallel, the lower their resistance is. These three resistors in parallel have actually a third of the resistance of just one of them by themselves. If you had that circuit there with just one resistor, that resistor has got 3 times the resistance of all three of them in parallel together like that. Okay, so answer B has got the most resistance, okay, which is not what we're looking for, and the one with the most resistors in parallel, which is A, is going to have the least resistance. Alright, so the correct answer there is A. Okay.